I'm Cayl Saga, a development engineer at Zircotec, and to give you a presentation on lightweight carbon fiber wheels and their thermal challenges. So Zircotec was founded on the transition from the nuclear industry to the motorsport and automotive. And what technology? It's specifically for ceramic technology that is a thermal management on parts such as exhaust and intakes. Thus, it was a natural challenge for tackling the thermal challenges of carbon fiber wheels. Carbon fiber wheels have gained significant attention in recent years due to the remarkable benefits of weight reduction. However, the concern is that the carbon fiber wheels have thermal issues caused by braking. And some parts of the wheel that is additively manufactured, such as the brake ducts, are made out of plastic and does also require a protection of our coatings. So the recent fascination of carbon fiber wheels is because they are light, and lightness means that we can get much more greater performance and efficiency. And if we compare it to the aluminium wheels would be around 25% more than the carbon fiber wheels, which means that because the wheel is actually part of the unsprung mass, it will allow for better design on the stability and handling of the car. Other parts can be made inside the wheel assembly can be made out of plastic, and this can be either from carbon fiber or of any 3D printed materials such as PEEK and nylon being the popular ones. The bigger problem of these materials is that they must withstand braking temperatures, and when you apply the brakes, friction is created between the brake pads and the brake discs and thus generate heat, and this heat dissipates to other parts within the wheel assembly. For road cars, you'll expect around 100 to 200 degrees, and for motorsport, you'll probably go around 600 plus degrees. But not all of the energy from and the temperature is not transferred specifically to all the wheels, to the wheel or to anything like the brake ducts. So you'll probably get, let's say, half of the temperature of 600, which will be around 300 degrees, but this is still way over the limit of the plastics that are inside the wheel, or the actual wheel itself. So the carbon fiber wheel would only withstand of around 100 to 150 degrees depending on the resin that is used, and for plastics you would expect for a high temperature plastic anyway 100 to 150 degrees. So this would mean the radiant heat from braking would lead to deformation and structural damage to anything that is plastic within the wheel. So how do we actually prevent this from happening? And it is from our thermal barrier coatings. Our thermal barrier coatings are a ceramic layer applied to a material. This is done by plasma spray. Plasma spray works by using gas to push from the plasma to push the ceramic powder into the substrate, such as the carbon fiber wheel. And whilst the powder is melted, so either gas or a liquid state, when it gets hit to the substrate of carbon fiber, it dries out quickly by either using quick cooling or just passive cooling, and essentially sticks into a ceramic layer. But the question is like, since we use this in exhaust and metal parts, which is easier and can withstand the plasma, can it not damage the carbon fiber plastics? It can if you are able to control the flame. So by quick passes, so fast speeds, you can essentially cool the plastic down quick enough so that the actual heat will only go up to a max of 100 degrees and allow for the ceramic to essentially stick to the material. So as long as the material can withstand 100 degrees, we can plasma spray pretty much any material, so any metal material, but it will just depend on the surface. So the plasma spray we use is a thermal barrier coating that is zirconia base of performance white. Performance white has a low thermal conductivity of 1.4 watts meter Kelvin and a maximum temperature of 1400 degrees. These are great because we are using this for the carbon fiber wheels and brake parts, and they allow for the operational temperature of these parts to be increased. So to validate our claims, we have some internal testing via thermal and flammability tests. So for our case study on the carbon fiber wheels, we did a simple carbon fiber plaque that was heat tested and shown that without the carbon fiber plaque, that it's exposed to a radiant heat of around 300 degrees. The non-thermal barrier coated plaque would go around 130 degrees, which is above the design limit. But with the thermal barrier coating, we see that the carbon fiber is well below the design limit and protecting the carbon fiber resin and allowing it to be structurally sound. For our next one is the flammability test for a brake duct. They use a plastic 3D printed brake duct and a simple flammability test, which shows that without the thermal barrier coating, the fire would easily pierce a hole through the plastic part, but without coating, it will not be able to create a plastic hole. So the ceramic technology is actually just not just used for thermal management. It actually has a lot of great uses. So ceramics can be used for dielectrics and, as you can see, flame proofing and EMI reduction for electric vehicles. The ceramic applied heat shield allows for a better way of insulating the heat inside the part and also protecting any parts outside of the coated heat shielded part. We also have abrasion resistant ceramics, which can protect the material from scratches and environmental damage and corrosion damage. And our thermal barrier coatings can also be color coated, that can withstand until around 980 degrees, which allows for better performance and also better looks, as you can see the various colors. Thank you for your time and for watching me talk about the case study of carbon fiber wheels and how we were able to develop and tackle the technologies of carbon fiber wheels.